So in number 28 here, we're dealing with a diprotic acid, we're dealing with a titration. You don't really have to worry about the whole titration curve. Since this is at the equivalence point, or after neutralization, in other words, we're really just dealing with stoichiometry here. You don't have to worry about that whole titration curve. You only have to worry about that stuff if you're not at the equivalence point, if you haven't quite reacted away all of the acid. All right, it's a diprotic acid. It doesn't tell us what diprotic acid. So let's come up with, well, let me just give you an example. You could do this problem with any diprotic acid, sulfuric acid, anything like that. But I'm going to write down H2A because since it's diprotic, there's two hydrogens and both of them can react. All right, if we're reacting it with KOH, that means that's going to go plus KOH. And you guys know that this is just a double replacement neutralization reaction. And so both H's will switch place with the K, and you'll form H2O plus K2A. The reason you have to have two K's on the A is because obviously the A is 2 minus if it's matched up with two H's. And so therefore the K has to crisscross with that, all right, to make the charges even out. All right, this isn't balanced. The balanced equation is going to be H2A plus 2KOH, and that's going to yield 2H2O. So you're going to make two waters from reacting away both hydrogens plus the K2A. All right, like I said, from this point forward, it's all stoichiometry. It really is. It's just stoichiometry to the very bitter end. I'm going to point out that when you do the stoichiometry, here's going to be your strategy. You're given a volume and a molarity for KOH. So if you have the volume and you have the molarity, let me write the equation. Moles over liters equals molarity. So we got the volume, we got the molarity, we can find the moles. That'll be the moles of the base, the moles of the KOH. Hey, that'll give us that. Once we find the moles of the KOH, we can use some fancy stoichiometry and get the moles of the acid. And once we know the moles of the acid, we're actually going to have to do a little bit of more solution chemistry to figure out what the number of moles that are actually corresponding to the 5 grams, because it's not actually, you notice there's this funny business going on with 25 milliliters and 250 milliliters. So actually, once we get the moles of this, that's not going to give us automatically the moles of the 5 grams, because only a tenth of the 5 grams was actually used in the problem. But anyway, that's the strategy. Get the moles of KOH, that'll get you the moles of acid, and from the moles of acid that you can eventually figure out the molar mass. All right, I'm actually going to do all this math out. So when I do the math, I'm going to get that 11.1 milliliters of the KOH over 1. I'm going to convert that to liters. And then I'm going to use the molarity. It's 1.0 moles per liter. That's the molarity again. So that can be a conversion factor. The reason I did this was just to get rid of the milliliters over here. And now the liters get rid of the liters, and that gives us moles, and I get 0.0111 moles of the KOH. All right, we've got to use stoichiometry now to figure out how many moles of acid. Well, you know that you're going to have twice as many moles of KOH as acid, so it's really just about dividing by 2. But we need to show the work to get that. So moles KOH over 1. And we're going to use the mole ratio, which is 2 to 1. So 2 moles KOH in the denominator, so it cancels, and 1 mole of the diprotic acid, H2A, in the numerator. That's going to show us that 0.00555 moles of the acid, H2A. All right, now, like I said, there's a little funny business going on with the concentration and all that kind of thing. So if we want to go find the concentration of the acid, which is the next step, we actually need the concentration of the acid. It's going to be moles per liter is the molarity. All right, we really do want the concentration here. The reason we want the concentration is because not all of the solution was used at the beginning. but the concentration of the solution at the beginning should be the same as the concentration of the solution you used. In other words, the concentration of the 25 milliliters should be the same as the concentration of the 250 milliliters. This isn't the only way to do this problem. This is the way I'm choosing to do it. So I'm going to go and plug in the 25 milliliters, which is actually what this is the number of moles of, because we only reacted 25 milliliters. So we're going to plug in that with 25 milliliters. And 25 ml is the same thing as 0.0250 liters. We're going to use the 0.00555 moles, and that'll give us our molarity, which happens to be 0.222 molarity. All right, like I said before, that's actually the same as the molarity of the 250 milliliters, so we can just use the molarity equation again to find out what the number of moles were. But you guys know that grams per mole, grams over the molar mass is the same thing as moles. So that's mass over molar mass. So I'm just going to plug that in instead. So the mass over the molar mass times liters is equal to the molarity. This is the molar mass. This is molarity. So this is a nice capital M, and this is like a script M. All right. So plug them all in. 5 plugs in here. The molarity plugs in here. That's 5 grams. The molarity plugs in there, and the liters this time is the 250 milliliters, which is 0.250 liters. In any event, at the very end, you're going to get 90.1 grams per mole. So 90.1 grams per mole is the end. All right. If you weren't able to do this problem by yourself, I really highly recommend that you go right now and do number 27. It's a very similar problem, and when you do it, I just wanted to point out that I looked up the answer for that, and I think it said 202. That's what I have written down. 202, I think. Let me pause and double check that that's the answer. I was right. It's actually 202 grams per mole. I got messed up because I didn't have the unit written down. A good reason to write your unit down always. So if you